In this lecture, we will be introducing the concept of convex functions. Suppose we have a function, f, that maps n vectors in Rn to real values r. We say f is convex if for any vectors x and y in the domain of f, we have the following equation. F evaluated at alpha x plus quantity 1 minus alpha times y is less than or equal to alpha times f of x plus 1 minus alpha times f of y for any alpha in the interval 0, 1. This is best understood by looking at a graph. So suppose we have Rn represented here on this horizontal axis. You can think of it as R1 for the intuitive purposes here. And then we have the range R up here on the vertical axis. First, let's think about the left-hand side of the inequality. Alpha is some number between 0 and 1. Think of that as a weight for taking a weighted average of x and y. If alpha is 1/2, this expression in these round brackets would be 1/2 x plus 1/2 y, the average of x and y. If it's something other than a half, it's just a weighted average that gives some more weight to one of the x or y than the other. So if we look on our horizontal axis, say here is our x and here is our y, then that weighted average of the two is somewhere in the middle. So this would be a depiction of our alpha x plus 1 minus alpha y. Now over here, on the right-hand side of the inequality, we see that we have a weighted average of f of x and f of y with the same weights, alpha and 1 minus alpha. Suppose when we evaluate f at x, we get something here. F of x. And suppose when we evaluate f at y, we get something, say, here. So this will be our f of y. And let's now think about what we have on the right-hand side of the inequality. This is that weighted average of f of x and f of y with weights alpha and 1 minus alpha. If alpha is equal to 1, this right-hand side is here at f of x. If alpha is equal to 0, then we have this right-hand side being equal to f of y. As alpha ranges between 0 and 1, we trace out this line segment here. Alpha parametrizes the line segment between the points x f of x and y f of y. Now coming back to the idea of alpha being fixed, when we fixed alpha, we had this value here for the weighted average of x and y, and we now have this value here for the right-hand side. The one thing we have left to do is to take this weighted average of x and y and plug it into the function, which we will do and now see the key to the definition of convexity. When we plug this into f, we have to get a value that is below that weighted average of f of x and f of y. So the value alpha x plus 1 minus alpha y plugged into f gives us a point that is lower than the blue point. And that is the key to convexity. Again, take this weighted average of x and y, evaluate f at that point, and you get something lower than the same weighted average of f of x and f of y. When you then step back for a moment and say, well, alpha could have been anything between 0 and 1, as we take this point here and just traverse across the interval from x to y, this relationship has to hold. This blue point, which moves along this line segment, will always be above the purple point. And the result is a graph that looks something like this. Put another way, this definition tells us that the line segment connecting the points x, f of x, and y, f of y, lies above or on the graph of, we'll say z equals f of x over the interval xy. I'm abusing notation slightly here because x and y are in Rn. But this is the idea. Anytime you take 2 points on the graph, if you connect them with a line segment, that line segment is above or actually touching the graph. And that is another way, intuitively, to think of convexity, a convex function. So a convex function has this property that we think of as concave up. So when you first learn calculus of a single variable, you encounter this with the idea of a function that is concave up. Now, along those lines, we can say that, as a theorem, if f, say, is just an ordinary function of one variable, is twice differentiable, and f double prime of x is greater than or equal to 0, say for all x in the domain of f, then f is convex. And again, in ordinary calculus of single variable, you would call this typically concave upward. So you can have a function, a convex function that looks like something here. Now it turns out this is the idea of strict convexity. So what we have here with this less than or equal to sign is actually the definition of convexity, but stronger. So we can say that f is strictly convex. And here we're referring to f from Rn to R, back to the original definition, if for any x and y in the domain of f, we have f of alpha x plus 1 minus alpha y and we'll use a different color here, is strictly less than alpha f of x plus 1 minus alpha f of y. And this is a little bit stronger of a condition. So in the definition that we gave at the beginning, if we look back at that, notice we said this line segment connecting these 2 points would be above or on the graph of z equals f of x. Being on the graph is when you have non-strict convexity. This secant line would never actually be on the graph itself. We can depict this looking at the case of strict convexity and non-strict convexity. For strict convexity, we have a function that looks something like this, like what we had depicted before. And we'll just think about functions of a single variable here. And for non-strict convexity, the difference is that you can have the function level off. So you may have something like this, where we have a flat spot. The definition of convexity is still satisfied by this function. But the difference will be if you pick, say, your x and your y here, then that secant line is actually right on top of the function. And you can't have that happen with a strictly convex function. And this sort of issue comes up a lot in optimization when you're minimizing functions, because here you see you would have a unique global minimizer, where here you would have a set of non-unique global minimizers. So this is the idea of a convex function and a strictly convex function. We also can do this when we think in higher dimensions. So a convex function as you would have learned it, say, in Calculus 2, for a function of 2 variables, would be something like a paraboloid. And we can't picture what a convex function would look like when we start to have a domain beyond R2. But the idea is still the same. Here, if you pick your x and y in the domain and look at the function evaluated at these points, then the line segment connecting the two is going to be above the graph. So any point on this purple line segment would be directly above the graph over this line segment connecting x and y in the domain. So again, convex functions intuitively are these functions that open upward. And again, anytime you take 2 points on the graph and connect them, that line segment is above or on the graph itself. And that's really the idea of convex functions. Now, there are some key theorems that we could look at in a separate lecture. There's another way that you can define convex functions in terms of support lines. But the key definition and the classical definition of convexity is this one. And the pictures we want to think of when we think convex functions are these two and this classic paraboloid type of picture.